Okay, so it's my pleasure to introduce Hossein Lamei Ramandi, who is going to talk about Galvin's question on sigma well-ordered linear, on non-sigma well-ordered linear orders. All right, go ahead.
Thank you for having me. So today we're going to talk about one of Galvin's questions from 70s. Let me talk about the background on this question a little bit. Okay, let's start with what sigma well-ordered means. A linear order L is said to be sigma well-ordered if it's a countable union of well-ordered suborders. For example, all well-ordered sets, all ordinals are sigma well-ordered, all countable linear orders are sigma well-ordered. Real types, which are uncountable subsets of the real line, are non-sigma well-ordered. Einstein types are not sigma well-ordered, and of course, omega 1 star is not sigma well-ordered. Galvin asked, does every non-sigma well-ordered linear order contain a copy of one of the following linear orders: a real type, an Einstein type, or omega 1 star? Recall that a real type is just a linear order of size LF1 which has a countable dense subset. So it basically has a copy of an uncountable subset of the reals. And an Einstein type is an uncountable linear order which does not have a copy of omega 1 star, and the closure of every countable subset is countable. Galvin was considering this question because I guess he was looking for a basis for the class of non-sigma well-ordered linear orders. So note that if the answer to this question was yes, then we would have a basis for the class of non-sigma well-ordered linear orders. But Baumgartner answered this question negatively. In fact, he found this example in ZFC, that if we take a stationary subset of omega 1 of limit ordinals, we take a ladder system indexed by the ordinals in the stationary set, and we put the lexicographic order on this linear order, then the resulting linear order is going to have the property that every uncountable subset is going to contain a copy of omega 1. It's not sigma well-ordered, and it's very wild in terms of minimality, which is if you take a stationary subset of S whose complement is also stationary, then L does not embed into L restricted to S prime. This was just a surprising example, and he was presenting this example in a paper called A New Class of Order Types.
Could I just ask, so how exactly is this thing ordered? You say it's ordered with lexicographical ordering, so you go, yeah. Why is this not well ordered?
Oh, it's not even sigma well ordered.
Yeah, that's what you're saying, but yeah, then I don't understand what you mean by lexicographical.
Yeah, it's the proof is the classical proof is I would not call it a trivial proof, and it's not the focus of the talk today. But I'm going to later issue and more created a machinery which is going to answer this question very quickly, why it's not sigma well-ordered. You can even say more. It's not sigma scattered even.
I guess I'm just not. I guess I'm not understanding how this is how the ordering works.
Okay. I'll make the ordering clear first. So we take a ladder system.
Yes, I know what all of that is, but what does it mean that the lexicographical ordering on this? Oh,
okay. The pen doesn't work now. Let me. What does it do? Let me reopen the whiteboard, the Paint application, and don't save this. Okay, here is the thing. So, okay, so we can, so you said that for every alpha in S, C alpha is a function from omega to alpha, which is cofinal. So it's a function. So we have a bunch of functions indexed by alpha, and we can say, okay, C alpha is less C beta, if and only if C alpha at n is less than C beta at n, where n is equal to the minimum k, such that C alpha k is different from C beta k.
Okay, I see.
This is
okay.
So the first place that they differ, we look at that component and
Mm-hmm.
see which one is above. And of course, whenever you are dealing with distinct C alpha, C beta, such an n exists.
Of course. Mm-hmm. All right, great, thank you.
The proof of the fact that, okay, so now, okay, now let's call LS to be this C alpha in S, and we put the order on this, and of course, or we call it L also. L restricted to S prime is just going to be the C alpha as alpha in S prime. So this is about the notation, but you're right. There's a classical proof with iteratively we can use the pressing down lemma and prove that, okay, this L is not sigma well ordered. If we can prove this, if S is not, if S is stationary, in fact, I can say S is stationary. That's if and only if LS is non-sigma well ordered. The proof is just using pressing down lemma repeatedly, but I don't remember the structure very well right now. But I'm going to introduce machinery, which is going to imply this very quickly. Okay. So this was Baumgartner's example. Because of this property of this linear order that I just mentioned, that if S and if S prime and S minus S prime are stationary, then LS does not embed into LS prime. Because of this property, at the end of Baumgartner's work, Galvin asks this question, and Baumgartner puts this question at the end of his paper too. Assume C is the class of all linear orders L, which are not sigma well ordered, and every uncountable suborder of L contains a copy of omega 1, which means that, okay, it does not have any real type, Einstein type, and omega 1 star. Does C have minimal elements? And they also mentioned that, okay, consistency results are also interesting. And this is exactly what happened. In around 2009, I guess, Issue and Moore proved that under PFA plus, every minimal non-sigma scattered linear order is either a real type or an Einstein type. So let's recall that, okay, linear order is sigma scattered. If a linear order is scattered, if it does not contain a copy of the rationals. It's sigma scattered if it's a countable union of scattered linear orders. And Okay, why does this theorem prove that Galvin's the answer to Galvin's question is consistently no? Is because of this fact, this fact which can be which is proved in the notes, but I'm not going to include the proof now. Okay, L is sigma well-ordered if and only if L is sigma scattered and omega 1 star does not embed into L. So if you have a sigma scattered linear order which doesn't contain a copy of omega 1 star, then it's going to be sigma well-ordered. The proof is included in the paper, but it's kind of tedious, so I'm not going to put it here. Okay. So basically, Issue and Moore proved that consistently the answer to Galvin's question is no. Well, now we want to prove that okay, it's consistent that there is a minimal non-sigma well-ordered linear order. Okay. One of the properties that the linear order that we are going to construct or generated by a forcing is that it does not have a copy of omega 1 star. So let's see what happens when a linear order or a lexicographically ordered omega 1 tree has a copy of omega 1 star. I'll mention that in the picture because that's more clear in the pictures than words. So suppose that we have an omega 1 tree like this, and it does not have any unenchanted subtrees, so it has a lot of branches. And our tree T has only omega 1 trees as well. So that's not very important, but the omega 1 trees that we're going to discuss today, they're going to have only omega 1 many branches. Because if any lexicographically ordered Kurepa tree is going to contain a copy of omega 1 star. So we are not allowed to work with Kurepa trees. If the set of these, if this, and our tree is so this is the tree, it's lexicographically ordered. And BT refers to the set of the branches. Okay, now if BT has a copy of omega 1 star, then we can conclude, the fact is saying that we can conclude that there's some branch B and an omega 1 sequence of branches like this, which are going up the branch like this. Their delta is going, so this is the peak size. Their delta with B is going to go up. And here, when you go to the right, we are going to get bigger with respect to lex. So this is a decreasing omega 1 sequence, and that's going to lead us to a branch. So you're going to have a branch and an omega 1 sequence of branches such that their delta with the original branch was going up. So if we can avoid this picture in our lexicographically ordered tree, we can make sure that our tree is not going to have any copy of omega 1 star. And exactly because of the same reason, every Kurepa tree is going to have a copy of omega 1. Every lexicographically ordered Kurepa tree is going to have a copy of omega 1 star. Any questions so far? Okay. Now we are starting to work on the machinery that Issue and Moore made several years ago. Assume L is a linear order. We say that L hat, so we use the notation L hat to refer to the completion of L. So for the by the completion of L, we just mean that, okay, assume, consider L and add all the detecting cuts of L to it, and you're going to obtain L hat. Now for any set Z and X in L, we say that Z captures X if there is some cut in Z intersect L hat such that Z intersect L has no element which is strictly in between Z and X. Note that Z is an arbitrary set, and we're interested in cases where this Z is a sufficiently large countable submodel of some H theta. And okay, here's what it means to capture. So we have this L, and we have the elements of Z. These are the elements of, let's say, Z intersected with L. And suppose X is here. If there is one cut in Z intersect L such there is no element in between X and Z, we say that Z captures X. If it does not such cut, we say that Z does not capture X. So when Z captures X, it means that Z has a best approximation for X. When Z doesn't capture X, Z does not have a best approximation for X. Going back to the lexicographically ordered trees and their branches and the case that we are interested in, which means that, okay, we have an countable submodel M here. We can say that a branch is captured by M if there's some branch in M which is going to get separated from this branch after delta of M. If there's not such a branch, then M is not going to capture that branch. I'm going to come back to this picture later, but I would like to implicitly say that, okay, this definition that Issue and Moore made can be transferred to omega-1 trees as well. But for now, I think this is clear. Okay. There's a very useful invariant for linear orders and omega-1 trees. So for linear orders in general, and I could adopt this invariant for omega-1 trees. I'm pretty sure if you work harder and you're interested in trees of higher size, you can adopt it as well. But in this case, we only need the omega-1 trees case, so we just focus on that. The invariant omega L is defined to be the set of all countable Z subset of L hat such that Z captures all elements of L. So we look at, so basically we look at all the countable submodels which are going to capture all elements of L, and then we put them in omega L. Gamma L is just going to be the complement of that. I would say the best invariant for understanding how large a linear order or an omega-1 tree is gamma of L, because a linear order is sigma scattered if and only if gamma L is non-stationary. And so let me, probably it's worth writing these facts because I have not included them in the slides. L, assume L is a linear order. L is sigma scattered if and only if L, sorry, gamma of L is non-stationary. And because we're working with linear orders and lexicographically ordered omega-1 trees, which do not have copies of omega-1 star, this is the same as sigma well-ordered. Also, if gamma of L minus gamma of L prime is stationary, then L does not embed into L prime. Yeah, so this is going to be a sufficient condition for contradicting minimality and other things. So this is a very useful invariant in understanding linear orders and omega-1 trees. Okay, so far we talked about linear orders mostly, but how can we adopt these notions for omega-1 trees? Assume T is a lexicographically ordered omega-1 tree such that for every T in T, there is a cofinal branch B, subset of T, such that T is in B. So this just means that T does not have any Arenshen comb, which is very easy to guarantee. And in all of the cases that we consider, this is going to happen. By gamma T and omega T, we mean omega of BT and gamma of BT, respectively. And BT is just the linear order on the set of the branches, which is going to be induced by the less order on T. Okay, here, very naturally, I just used the linear structure on the branches of the tree T in order to make omega and gamma. But I would like to mention that for the trees, it doesn't matter which lexicographic order you're going to put on that. At the end, when T is an ever-branching omega-1 tree, if T is an ever-branching omega-1 tree, and B is a cofinal branch of T, M counter-node submodel of H theta, which is sufficient. T and BT, etc., are in M, so I'm not going to write that. Then M captures B if and only if there is some C in BT intersect with M such that delta of C and B is at least M intersect omega-1. So it doesn't matter which lexicographic order you're going to put on that. Okay, we already talked about this. We already, I think, mentioned this fact that L is sigma scattered if and only if gamma L is not stationary in this structure. So we're just going to pass. Okay, based on these notations and machinery, we can rephrase Galvin's question this way. Does there exist a lexicographically ordered omega-1 tree T such that the following holds? 1, T has no Arenshen subtrees. Every uncountable subtree of T is going to contain a branch. For any B in the set of the branches of T, there is alpha in omega-1, such that if C is a branch of T, then delta of BC is above alpha. If C is a branch of T, such that delta of B and C is above alpha, then C is less than B. This is just saying that this picture is not going to happen. This picture that I had here is not going to happen. There is some alpha for every branch B. There's going to be some alpha after which there is not going to be any other branch which is branching to the right. So let me, because that picture is not very clear. So for every branch, there exists some alpha, after which anything that is branching from B, that's going to be to the left. So after this point, this is not going to happen. Okay, this is going to take care of copies of omega 1 star. Okay. 3 is saying that if L is a subset of the branches and it is nowhere dense, then gamma L is non-stationary. Okay, if this happens, then every nowhere dense subset of L or every nowhere dense subset of BT is going to be sigma well ordered. Because when gamma L is non-stationary, L is going to be sigma scattered, and because it does not have a copy of omega 1 star, L is going to be sigma well ordered. If L is somewhere dense, then the set of all branches embeds into L as a linear order, of course, just consider with the Lex order. So in this case, B, the set of the branches is going to be minimal among the somewhere dense set linear orders. And of course, we want BT to be non-sigma well ordered. So we have to make sure that gamma of T is stationary. Because if gamma of T is non-stationary, then it's sigma well ordered. But we want it to be non-sigma well ordered. If gamma of T is stationary, and then BT is going to be non-sigma well ordered, and because this is going to embed into all of the somewhere dense sets, all of the somewhere dense sets are going to be non-sigma well ordered as well. So the picture of, with respect to the invariant, is going to be something like this. We have an omega 1 tree. This is BT. And for every L subset of BT, there are two cases. One is that L is nowhere dense. In this case, L is sigma well ordered. And of course, gamma of L is non-stationary. The second case is that L is somewhere dense. So because gamma of L, because gamma of T was stationary and BT was embedding into L, this means that gamma of L is just equivalent to gamma of BT, and gamma of BT or gamma of T is stationary. This means that we have one stationary set gamma of BT such that every subset of BT is going to have gamma trivial here, equivalent to the empty set. It's going to be non-stationary, or it's going to be equivalent to the whole thing. Either it's the whole thing or it's nothing. So it's like it's a gap. You can't go up and down when you vary the subset of BT. It's just there are only two cases for this linear order. Okay. Note that this is in contrast. This is in dramatic contrast with the case of Baumgartner's example. Okay, this is a good point actually to talk about Baumgartner's example a little bit. For instance, when in Baumgartner's example, when I had LS, gamma of LS was exactly S. What do I mean by that? Suppose that M is a counter-Lorentz model of H theta, and yeah, then M is in gamma of LS, or maybe I should put that M intersected with the L hat, but okay, let's forget about that. M LS hat is in the gamma of S, gamma of LS, if and only if M intersect with omega 1 is in S. This is why, okay, now we can see that if S is stationary, gamma of LS, S is stationary if and only if LS is not sigma well ordered. We can also see the other fact, this fact that it behaves very strangely it behaves this way with respect to minimality, that if S prime and S minus S prime are stationary, then LS is not going to embed into LS prime, because then in this case, gamma of LS is going to be strictly above gamma of LS prime. So here, there's not such a gap. If you reduce one element from a few elements from S, that's going to affect gamma. But in the linear order that Galvin is asking, some behavior like this is going to happen. There's a gap. Either you have the gamma is the whole thing, or it's nothing. Okay. Okay, we start by, so we are going to start generating this lexicographically ordered omega 1 tree by this forcing that we see here. The forcing is called Q, and we're going to call it Q for the rest of the talk. The elements in Q, the conditions in Q have 3 parts. The first part is a tree. The second part and the third part are functions that are described as follows. So let's start with the tree. So this is TQ is just going to be a lexicographically ordered countable tree of height alpha q plus 1. So it's going to have a top level with the property that for all t in TQ, there's an element on the top level such that t is less than s, which we picked from the top level. Here, lambda is just some fixed set, arbitrary, pick your favorite uncountable set, and you're just taking we're just picking that set to pick elements. There's nothing important about that. And we make the lexicographically ordered level by level. So there is no order on lambda. Just to clarify, nothing is going to be, if there is an order on lambda, that's not going to be transferred on the tree. You're going to make the lexicographically ordered by the conditions, level by level. The second part of the condition, BQ, is a bijective map from a countable subset of omega 1 onto the last level of TQ. So far, the conditions of Q are very similar to the very well-known forcing that creates a Kurepa tree. If we forget about DQ and we substitute omega 1 by omega 2 and we assume CH, then this poset is going to create a Kurepa tree. But DQ is going to play an essential role. Let's see what DQ is. For every element on the top level, we are going to have some alpha from the domain of BQ, which is mapped to that top level. DQ is going to associate another ordinal in omega 1 to that ordinal, which is going to take care of branching to the right. After that alpha, we don't want the alphath branch to have other branches which are branching to the right. So maybe this is better to draw the picture. So this is the condition TQ. It has a top level, and we have a T here, and we are going to have some alpha. So BQ is going to send some alpha to this. dq is going to associate, so when dq of alpha is, let's say it's psi, and let's assume that psi is less than the height of q, then we are going to have this property that after psi, there is not going to be anything which is branching to the right. This is not allowed anymore in this tree. So this is not allowed. Anything which is branching from this branch here has to be to the left. We are allowed to go to the right before psi, but after psi, it's not allowed. So dq is going to take care of that. And it's important to mention that when we forget about dq and we assume ch, we can easily substitute omega-1 by omega-2. The resulting forcing is going to satisfy the LF2 chain condition, and it's going to create a Kurepa tree. But if we keep dq and we substitute omega-1 by LF2 or omega-2, and we apply this forcing, we're going to collapse LF2. So dq is adding some obstruction to this forcing, and this forcing is not as flexible as the well-known forcing for creating a Kurepa tree. Okay, maybe it's a good time to ask if people have questions. Okay.
Maybe these trees, how many successors? I mean, are they uniform in some way? Does every node get the same number of successors, or is that
not necessarily?
Okay.
If you can always use genericity, I could add it.
Okay.
Add that property to that, but this forcing and the definition of order on it is already big, so you can conclude those properties by going high enough and use genericity to get this.
Mm-hmm.
But that's very used actually in the proofs, because we are interested in a lot of copies of the rationals when you consider the elements of the tree at some level. We are interested in a lot of copies of the rationals, but that's guaranteed by genericity.
Okay.
Cases. Okay, let me describe the order on this forcing. Extension on the tree is just the end extension, so we assume that, okay, Q is a stronger condition than P if it has higher height than TP, and its restriction up to the height of TP is the same as TP. It has the same elements, it has the same tree order, and it has the same lexicographic order. And we want domain of BP to be a subset of domain of BQ. So the domain is going to be bigger. And we also want that, we also want this picture. So considering BQ, so suppose that this is TQ, the bigger condition. We have this TP, the smaller condition, and we want that if BQ of alpha is this guy, and BP of alpha is this guy, then I want this to be less than this. So at the end, when I look at the BP alphas in the generic filter, that's going to create a branch, a cofinal branch for the tree. So in fact, so this is going to have this property that in the generic filter, maybe I should say for the generic filter, we have this set BP alphas P in G is a branch, a cofinal branch of T, and we call it B alpha. And these are going to be the only branches of the tree. So we can also prove that if T is the generic tree for this filter, the set of all branches of T is the B alpha such that alpha is an omega 1. So we're not going to produce any extra branches that we have not predicted. And okay, well, in the extension, we just assume that DP is a subset of DQ. So we are going to be faithful to the commitment that we have made at P when we want to extend to Q. Okay. Any question about the order of the forcing? Okay. This lemma 1, the statement is pretty long. It is basically saying that this forcing is the forcing that we were talking about. Oh, and by the way, this forcing, the forcing Q that I just mentioned is going to have the LF2 chain condition if CH holds. That's just the same as the proof for the well-known forcing for creating a Kurepa tree. It's going to be sigma closed as well, but we need more than just sigma closedness. We want, we are interested in different kinds of, whenever we're given some counter decreasing sequence, we're interested in different kinds of lower bounds. Assume that Qn is a decreasing sequence of conditions in Q, and M is either a Nash number or it's omega. And for every element of M, we're going to have some branch of the union of TQNs. So we have a sequence like this. We have a sequence of QNs. And when we take the union of all these, because these are decreasing sequences, these trees are end extensions. So their union is going to lead up some countable tree without a top element, right? And this tree, of course, has continued many branches. There are two types of, so we have a bunch of branches which are indexed by the domain of BQs of these conditions. So these are QNs, so TQNs. Let's call B psi here to be the BQN of psi. N in omega. This is going to give you a cofinal chain of the tree. By cofinal, I mean it's going to go up to the highest levels, as high as you want. It's not going to be literally a branch, but it's going to go as high as you want. So, and it's going to be a chain. For psi in the union of the domain of the BQNs. There are also CIs. And let's assume that CIs are different from these. This sequence might be empty, but we're going to discuss that what happens if this sequence is empty, what happens if this sequence is not empty. Okay, and the lemma is saying that we can act as freely as we want. No matter what, no matter what the sequence of CIs are, as long as they're countable, we can add top elements for the CIs and BQs, big size, and have a lower bound for the sequence. So if this is empty, if the sequence is empty, this sequence is empty, this is very easy. We just put a top element on top of every big size, and that's going to create a condition. If this is not empty, and these are cofinal in this tree, we're still going to be able to put some element on top of that. This is again tedious, but it's spelled out in the notes if you're interested. But this is the content of this lemma. And why do we care about this? The reason is that suppose, the reason is this situation. Suppose we are given some countable elements of model, and we have this is M, and this is an MQ generic sequence of conditions. So this is Q and TQNs, and QN, and in omega is MQ generic. If we define a lower bound, of course, because it's sigma closed, we can find there is a lower bound Q for QN. Okay, if we define this lower bound, assuming that the sequence CI was empty, if Q is if you're not generous in adding two extra branches to this, and if we assume that the CI is empty, if CI M is empty, then Q is going to force that M intersected with the set of BT is in omega T. In other words, M is going to capture all elements of all branches of T. Why is that? It's because by genericity, every psi in M is in the domain of BQN for some N. Then what happens is that, okay, in the extension by this Q, the top level of this truncation of this tree is going to be only the elements which are going to be in some big size. So this means that so let's assume that M intersect omega 1 is delta. Then under this situation, T delta is going to be the set of all big psi at delta. So this means that the element of big psi, which is of height delta, such that psi is in M intersect omega 1. So this is going to be the level T delta. Now pick an arbitrary branch of this tree T. The delta element of that branch is in T delta, of course. So, but big psi so there's going to be some psi in M intersect omega 1 such that big psi of delta is that element. So big psi delta of that original branch that we took is going to be above this ordinal. So M is going to capture every branch. And this means that, okay, M is going to be in omega, but what we mostly care about the M's which are in gamma, because we want to make sure that the ultimate the ultimate set of branches in the extension, that's going to be a large set, that's going to be non-sigma well ordered. So the question is, how can we make sure that M, so the question is how can we make sure that M intersect with BT is in gamma of T? So we want a condition which is going to force that. So in fact, we're going to work on different kinds of lower bounds for this. And now, it's by the same argument that I just showed, that by the genericity that I use and the fact that the T delta is going to be this, if I choose this to be non-empty and define this Q for Ci, which is non-empty, then that Q is going to force that M intersect with BT is in gamma T. So my point is that if Ci, I, and M is non-empty, and of course we're going to assume that it has elements, it's disjoint from the set of big size, then Q is going to force that M intersect with BT is in gamma T. Is this clear based on the argument that I already made, or should I include a proof for it?
I think it's good.
Okay, it's good. Great. Okay, actually, I'm not presenting proofs here. I'm just talking about the ideas. If the ideas are clear, I'm happy. Okay. Again, by the same argument that I just talked about, we can show that gamma T and omega T are stationary because we're free in finding lower bounds for MQ generic sequences. So we know that they're both stationary. BT has a copy of Baumgartner types, which we have to kill. Okay, we're not going to use this fact, but it's good to know that in the generic extension, we are by Q, we are going to have some elements like this. So suppose that we are in the extension by Q, and this is just the generic tree. This generic tree is going to have some elements like this, like element like this. For these elements, there are counter-element submodels M, which are not going to capture these guys, but when we look at the elements below them and any other counter-element submodel N is going to capture the restriction of this element to their height. So they are kind of the first elements which are not captured. And this is happening stationary often. The set of alphas at which these elements are going to occur, this is going to be stationary. And when I add up all of these elements into one set and put them the lexicographic order of the tree T, they are very close and similar to Baumgartner's examples. You can cook up some ladder systems which are going to be copies that are going to be like Baumgartner's example, and that's very bad because Baumgartner's example we're making that gap very hard to make. As soon as you shrink the stationary set a little bit, their gamma is going to shrink. So we have no other way except for killing all of them. We have to make all of them sigma well ordered. But then we have to make sure that we're making some non-sigma well ordered linear orders, sigma well ordered, but we have to make sure that the whole linear order is going to remain non-sigma well ordered. And this is going to be the main challenge for the rest of the talk, I guess. Also about this tree, we can say that every uncountable downwards closed subset of T contains some big psi. That's already mentioned in the picture. So, okay. So we had D, but this D was sometimes artificially high. We have to make it a little bit lower which is this dig psi, this new dig psi. For every psi in omega 1, dig psi is going to be the sup of the delta of big psi and b eta, such that big psi is less than b eta. So this is what is happening here. So suppose that we have this generic tree, and we have big psi. We look at the sup of the ordinals at which there is some branch to the right. And of course, this is going to stop somewhere before omega 1, and this is going to be the d of big psi, or d of psi. We use d psi on d big psi or db interchangeably. The function d is countable to 1. And this is the main reason that if we substitute aleph 1 by aleph 2, we are going to collapse aleph 2, because this d is countable to 1. And of course, this is going to collapse aleph 2. And it's very easy that this d is countable to 1. Also, for every t0 in t and beta above height of t, there is an alpha above beta, such that t alpha above t sub t0 contains a copy of the rationals. So this is saying that whenever you have an element of t, if you go high enough, suppose that this is again the generic tree t. This is t. It's saying that there's some beta high enough such that whenever we look at the elements above t at height beta, this is going to contain a copy of the rationals with respect to the Lex order. Of course, we cannot say it's going to be isomorphic to the rationals, but it's going to have a copy of the rationals, because, for instance, if you have branches here whose alpha are less than beta, then this is not going to be a copy of the rationals. It's impossible to make it a copy of the rationals. Okay, but we don't need exactly copies of the rationals. We just need those cones to contain a copy of the rationals. Okay, here's how we make copies of Baumgartner's linear order, sigma well ordered. As you know, we have a characterization of sigma well ordered linear orders in terms of stationary sets. So all we need to do is to shoot clubs in some stationary sets. So SL is a forcing which is shooting a club in omega of L. So whenever some alpha is in omega of L, so yeah, this is just countable sequences with a top element, and they are coming from the omega of L. So we just shoot a club, and as you know, they're not proper, but they preserve omega 1. So in the iteration of these forcings, we need to be careful. Assume X is uncountable, and S subset of the countable subset of X is stationary. A poset P is said to be S complete if every descending NP generic sequence has a lower bound for all countable submodels M, which are coming from X. So in the definition of properness, we were saying that, okay, for every M, for instance, if we say for all M and for all Qn NP generic, there exists a lower bound. There exists a Q such that for all N, Q is less than or equal to Qn. This is stronger than properness. But if we say that for all M that are coming from S, and S is some stationary set in the countable structure of X, S is a stationary set in here. If we say that this is not stronger than properness, this is even not. But with respect to countermoment submodels which are coming from S, this poset behaves like sigma closed posets. Okay, now we are ready to talk about the forcing, which is adding embeddings from the whole set of branches to the somewhere dense sets. Okay, these posets have two parts, FQ and phi Q. FQ is going to be some partial tree embedding, which means that, okay, we take the truncations of the tree and we restrict it to some sets of ordinals AQ, and we send it to the corresponding levels of the subtree that we considered. It has also some correspondence between the branches by phi Q. So the first condition is going to explain the requirement for FQ, and the second condition is going to explain the requirement for the correspondence between the branches. And of course, this FQ and phi Q have to be consistent with each other. This is explained in condition 4. The very important condition 3 here is that, okay, for all t, so again, it's better to talk in terms of pictures. So we have this tree t. So this is t. And we have a subtree of tu, which is because we're dealing with somewhat dense subsets of BT. When you take downward closure of those, when you look at the union of those branches, that's going to be a downward closed subtree of T. So this is a subtree of T. The conditions are like this. So we have some levels. We choose some levels. So this is going to be the set of AP, and FP is going to be from this tree which is restricted to AP to U restricted to AP, which is going to preserve the Lex order and the tree order. And the important thing is that, okay, this AP is going to have a max. It's countable, closed, and it's going to have a max. So this truncation of the tree is going to have a top level. The second part is a correspondence between the branches. Again, these branches, this phi p, so this is going to take branches by phi, and this phi p is going to preserve the Lex order. It has the property that when you look at the branch and you look at this, the restriction of that branch at the height of the maximum of AP, this has to be the same as how FP is sending this. So for instance, if phi is sending this branch to this branch, then FP has to send this element to this element. Also, we need the requirement that whenever I pick one element on the top level of this condition, there are only finitely many branches which are in the domain or in the range. Because if there are countable, if we allow infinitely many branches, we're going to get stuck in density. So we are only allowing finitely many branches so that when you go high enough, we have enough room to play with the forcing. And condition 5 is going to take care of D. Of course, if we send a branch, if D of this branch is higher than D of this branch, then we are going to get stuck on how we are going to deal with elements that are branching to the right here. So we want that the D of the image is at least the D of the element in the domain. So this is condition 5.
So AP is a set of ordinals. Is that right? Or
AP is a set of ordinals.
okay.
AP is the set of the levels. T, the elements of T don't matter what they are. We fix the lambda in the beginning, and that's going to be the elements of the tree T. The extension for this forcing is going to be as natural as you can imagine. We are going to extend AP by end extension. So AP is an initial segment of AQ, FP is a subset of FQ, and phi P is a subset of phi Q. So it's just a natural extension of this. And this forcing is going to have the properties of density, and of course I'm not going to talk about them here. Okay, this is the density for this forcing are kind of they might look non-trivial, but they are not hard. They're just a bit tedious, and that's spelled out in the notes. So I'm going to skip it. Again, this is density. The forcing EL is omega T complete. This is probably useful to talk about a little bit. Okay. Both SL and EL are omega T. The reason is for, let's start with SL. So SL was just a sequence of ordinals. So we have a countervalence submodel M, and we have a tree, we have our tree. And when we look at T, and this is M intersect with omega 1, is delta. And when we look at the T delta is going to be big psi at delta. Psi is an M intersect omega 1. Okay, now we can just, so an MQ generic, an M, so an MSL generic sequence is a since this is cofinal in delta, we can find a lower bound for this sequence if and only if we can put delta on top of that. And because M is going to capture everything, that's no worry. We can just put delta on top of that, and that's this ordinal is going to be in omega of this L as well, because this ordinal was in the omega of T, and omega of T is going to contain is going to be a subset of omega L. When you
could I just interrupt? It's probably a silly question, but so you're basically you're in the forcing extension where you added this particular tree T now, right?
Yes.
And you're doing another forcing there now.
Exactly.
Okay, right. Yeah.
Yes. For EL, the situation is similar. When we are in omega T, the situation is very easy. because of this property. Because of this property here. The challenge when we want to find a lower bound for the sequence of elements in EL is that, okay, how to send the elements of the top level to the elements here. But because of this property, that's already decided by the generic sequence. Because by genericity, every psi in M intersect omega 1 is going to be in the domain of some phi q, and that's already decided. So that's easy. When we want to find a lower bound for EL and SL and make M to be in omega, that's pretty easy. The challenge is finding a lower bound and making M into gamma. Okay. And this is going to be the content of the rest of the talk, basically. So this is the iteration that we're going to work on. We start with a model of CH. First, we force with Q, and then we force with EL and SL by a nice bookkeeping function. So maybe that makes sense to. So the forcing is going to look like something like this. So we start from V, and it's going to satisfy CH, and we start from V, and then this is the iteration P. So this is the P we want to talk about. The first instance is just Q. We add the tree, and after the first step, we just put ELs and SLs. If L is somewhere dense, we put EL. If L is nowhere dense, we put SL. And we take the bookkeeping so that every L subset of BT is going to appear. Okay. Now, so in the forcing, is going to be something like, first we are going to add a tree, and then either we are adding an embedding or we are shooting a club. I would like to mention that even these ELs are going to shoot clubs. These are improper. ELs are improper. SLs are improper. But when we look at the whole iteration P, that's going to be a sigma closed poset. So it's an iteration of a bunch of improper posets, but the whole thing is going to be sigma closed. Okay, so we are going to preserve omega 1 because, okay, it's sigma closed, but we have more clear machinery to prove that. The first poset was sigma closed, and the rest of the posets were omega t complete. So they're going to, so ELs and SLs are omega t complete. So not only they're going to preserve omega 1, but also we can say that in the final model, the set of the branches is going to be the same as this first model that we had created. So in the rest of the iteration, we are not going to add new branches. In the rest of the branches, this is again by finding different kinds of lower bound for MQ generic sequences. But because this talk is taking a bit longer than what I was expecting, so I'm not going to go through the proof. But the idea is, again, finding different kinds of lower bounds. So we're going to have, we're not going to add extra branches, and we're not going to add Arnschen subtrees. So no extra branches. And also no Arnschen subtree.
So you're doing a countable support iteration?
Yes. Thank you. Okay. Again, if we, so again, we have this iteration. We're going to take a counter-submodel, which is going to contain this iteration M So we are going to find lower bounds for the first instance of this iteration, and then lower bounds for the indexes of the iteration which are in M intersect with omega 2. So that the length of the iteration is, of course, omega 2, by the way. Okay. How do we do this? So as I said, let's take a counterweight submodel M, which is going to take, which is going to have the iteration, and let's take an MP generic sequence in this for this model. Let's take the first coordinate of this sequence to be Qn. That's going to introduce us the truncation of the tree, of the generic tree. Okay, now, again, we're dealing with the same scenario as before. Okay. We're going to be in the same scenario. We have this branch, we have this tree, countable tree here without a top element, and we have this countable submodel, and we have the iteration ELs and SLs. If we, when we look at this, so this is Pn and in omega is MP generic, and Pn restricted to 1 is Qn, and this tree is going to, we are going to call this tree, so R is going to be the TQNs in omega. Okay. Now, if we only look at the size, which are already in M, and we put a top element on top of big size, we can easily find a top element for the rest of the iterants. But if we do that, the resulting lower bound is going to force that M is going to capture all elements. What we need to do is to diagonalize over all of the branches which are already in M. So we're going to have extra branches here. But when we have extra branches, there are two worries about them. What if this extra branch is in the closure of some nowhere dense set? Then we cannot put the height of M into the generic sequence regarding that SL. The second worry is that what if this branch with the extra branches that we have added are not closed with respect to the functions FP and phi P in the SLs? Because we want, when you have extra top elements, you want those top elements to be sent to some elements in these branches SLs and so the elements of these are like phi P, FP and phi P in here. You want the extra branches to be sent to something by these. Okay, the way we deal with this is that, okay, we diagonalize over the branches which are already in M in such a way that, one, we are after, for every branch which is in, at every step that we are extending, because when L is nowhere dense, there, for every element here, there's going to be some element on top of that, so that this cone is not going to intersect the downward closure of this L. So at the extension, I'm going to go into that cone. So I'm not in the closure of any nowhere dense set which is indexed in M. For the closure with respect to the ELs, I'm just taking the Skolem closure of all of these FPs and phi Ps, so that my at the end, I have enough top elements to send my elements that I've added. Also, at each step, I'm going to take care of the requirement that I'm different from some big psi. So my branch is going to be different from some big psi. So at the end, first I'm adding one single branch, which has the property that, okay, after some, for every nowhere dense set, which is already in M, it's going to go into that cone that I just draw. Second, it's going to be different from the nth big psi. Third, it's going to be, and when I'm done with this, I'm going to have one single branch, which is good enough for this column closure. After I have the good enough branch, I take this column closure, and by induction, I extend the rest of the rest of the iterants of the conditions. And this finishes the proof that M intersected with BT is in gamma T. So we could say that gamma T is stationary. I hope that the ideas were clear, but if it was not clear, please ask questions. I'm done.
Thank you. Great talk. That was really good. I think, you know, with your sketches on the whiteboard, it was much better than reading the paper.
Thank you.
Great. Okay, are there any questions for Hossein?
I don't have a question. I have a comment.
Okay.
Yeah, that the person who really would enjoy this talk was Hausdorff.
Oh, thank you.
Yes, I mean, except for the forcing, everything, you know, the particularity about, except for the forcing, everything is things he would have, you know, latched on to.
I'm very glad to hear that. You made my day.
My pleasure.
Yeah, this idea of characterizing properties of this of the linear ordering by looking at the stationarity or non-stationarity of gamma of L and omega of L and all that is really interesting. I wonder if there are other things you can characterize by, you know, in a similar way.
I agree with you. I agree with you that the Justin and Tetsuya made this, and it was not I was initially thinking that it was that Justin and Tetsuya were the first people who thought about trees and linear orders in terms of the counter-limits model, which are capturing elements, etc. But okay, they did a lot of work. They proved a lot of interesting facts, which are all of which are not included here. For instance, they proved that if they have some characterization about external element, internal elements. If you have, for instance, one element which is external to some element countable in some model in some linear order or in some omega-1 tree, that's going to give you an Einstein suborder. In their paper, in the fundamental paper, they proved all of these facts, which were very interesting. I'm sure that those facts, they found those facts as the first people. But when I came to Toronto, Stavo gave me a handwritten note that a lot of years ago, he had thought about the countable limits of models which are capturing trees and linear orders, etc. He did not prove the facts, the interesting facts that Tetsuya and Justin found. But he had started to think about countable submodels which are capturing, and in fact, he was using the notation of the norm of a tree, and that actually led us to a project which was finished last summer, proving the consistency of it's consistent that every Kurepa tree has an Einstein subtree.
Oh, okay.
We used that machinery, the machinery of Tetsuya and Justin in that paper.
Very interesting stuff. Okay, any other questions or comments? Okay, well, thanks a lot. Great talk.
Thanks for having
me. Really enjoyed it.
Okay. Have a great